Good afternoon, chemistry class. Today we're going to be discussing
chocolate rain.
Close te Zandi. Actually, we're going to be discussing acid rain. Most of us have heard of acid rain, but not everyone knows where it comes from or how it's formed. Let's take a look, shall we? The production of acid rain begins when the chemicals sulfur dioxide, SO2, and nitric oxide, NO, are released by the burning of fossil fuels like those used to power factories and motor vehicles. These two chemicals travel high up into the Earth's atmosphere, where they react with atmospheric compounds that eventually create acid. In order to get a better understanding of how these compounds become acids, we're going to need to take a closer look at the chemistry. Sulfur dioxide, SO2, combines with atmospheric hydrogen peroxide. To form SO3 and water. After we form SO3, we're going to have a reaction between the SO3 and the water to form sulfuric acid. On the other hand, nitric oxide can be converted to nitric acid by one of two ways. First, nitric oxide can react with hydroxide ions in the atmosphere, along with ozone, to form nitric acid and oxygen molecules. Secondly, nitric oxide can react with hydrogen dioxide to directly form nitric acid. Now you may be asking yourself, how does acid rain affect the environment? Acidic solutions increase the corrosive effect of oxidation for some metals. This increased rate of oxidation not only destroys the superficial beauty of metals, but their structural integrity as well. Oxidation occurs when electrons are transferred from one atom or compound to another. In the case of iron, we have 6 free-floating electrons, which are going to be transferred to the 6 holes in these 3 oxygen atoms. This reaction yields Fe2O3, commonly referred to as rust. As with oxygen molecules, electrons can be transferred from iron to sulfuric acid ions. In this case, iron 3 sulfate is formed. So as you can see, the more acidic a solution is, the more metal oxidizing reactants there are. According to the DEC, the acidity of rain falling in New York State is nearly 30 times greater than it should be, with an average pH of 4 to 4.5. Knowing that, it's quite fitting for New York to be among those states known as the Rust Belt. Oh there. I'm not very good at playing the cello, but it makes for a wonderful analogy. A finely tuned instrument is a lot like life, in a biological sense. The G string we'll call that food and water. The D string, we can call that temperature. Every organism needs an ideal temperature to operate at. The A string, let's call that one pH. Now life, a lot like a finely tuned instrument, requires these all to be in the perfect pitch, so to speak. And if you adjust one of these too much, then you could change everything for the worse. And the instrument would be unplayable. Let's see what happens when we change the pitch of our pH for some microorganisms. In order to demonstrate the effect of pH on life, I headed up north into the Adirondacks, where I suspected I might find some microorganisms. In my attempt at finding life, I simply searched for the smelliest body of water I could find. However, in spite of my professional extraction, I ultimately had to ask the professor of biology here at FMCC, Michael McDarby, for some of his microorganisms. For the experiment you're about to see, we're going to be observing microorganisms in their original solution, in an acidic solution, and in a buffered solution. I began the experiment by testing the initial pH of the water, which turned out to be somewhere between 6 and 7. Before playing around with the acids or buffers, I wanted to get an idea of what we'd be seeing. I took a sample from the beaker, placed it on a slide, and found myself a little microworm. As you can see, it's moving about quite vivaciously. After taking a look at the microworm, I then prepared my acid solution and my buffer. In order to mimic acid rain, I titrated 1 milliliter of 5 times 10 to the negative 3 molar sulfuric acid into a 100 milliliter sample of the pond water until the pH was about 4. Next, I made a 0.1 molar buffer by adding 0.84 grams of sodium bicarbonate to 100 milliliters of water. Now it's time to expose our microorganisms to acid. Note the sporadic aimless movements of the worm. After a few moments, this casualty of science gave up the fight against a low pH. I wanted to see if it would be possible for life to live in a solution where the pH had been buffered from a low pH to a higher one. To do so, I titrated the sodium bicarbonate until the solution returned to the original pH of the pond water. To determine the pH, I cheated a little bit and used a pH strip for every 2 milliliters added until the pH had become nearly neutral. You can see by this little fellow here that the solution has been successfully returned to a state of biological viability. Okay, so we know how acid rain damages our planet. So what can we do about it? The answer to that question may be a little disheartening. It isn't likely that we'll stop driving our cars or halt the production of electricity for the sake of reducing acid rain. It may seem as simple as, just buffer water that's been acidified, right?
Wrong.
Indeed, there have been some projects where large quantities of limestone have been added to acidified water to buffer and neutralize it. However, the process of reversing acidification of large bodies of water is very expensive and time-consuming. In truth, the best measures we can take are preventative ones, that is, improving the effectiveness of smokestack filters in industry and exhaust filters in cars. There are no better preventative measures, however, than finding a safe, clean, and efficient alternative energy source. Although we're currently utilizing many alternative sources of energy, such as wind power, nuclear power, and solar power, none of them fit neatly into all of the desired categories of safeness and efficiency. To achieve this, it's up to those working in alternative energy sciences and engineering to discover the ideal method for powering our world. We may be surprised by what's to come.
Oh man, all this talk about acidity has kind of got me feeling